We now move on to the second important laser out of the three, which is the carbon dioxide laser. So we first look at a few special features of this laser. It is the first molecular laser, meaning all the lasers which were invented before this were usually atomic, meaning they dealt with one type of element. So if I say gallium, just gallium, or if I say silicon, just silicon. So carbon dioxide is where the first molecule was used in a laser as the active medium. Emission from vibrational levels, we will look at vibrational levels in a minute, and IR emission, so your output light is going to fall in the infrared region. It was developed by C.K.N. Patel from the Bell Labs. Active medium is carbon dioxide gas, so the main active medium in your CO2 laser is the CO2 gas. The CO2 is where this movement of electron from this level to that level and all that happens. You also have nitrogen and helium along with CO2 for specific purposes, namely resonant transfer and depopulation, which we will look at in detail in a minute. Pumping mechanism, electric discharge. So electric energy is used to perform the pumping or the population inversion. Pumping scheme, transfer to metastable level, which is a vibrational level. So I think this is a good time to pause and understand what are electronic, vibrational and rotational energy levels first, and then we'll come back to the CO2 laser. So throughout this chapter we've been looking at energy levels, and when I say energy levels, most likely the picture that comes to your mind is a set of parallel lines, horizontal lines, something like this, where each line represents an energy level, and some are occupied by electrons, some may not, and the electrons are moving between them and so on. So which is right, which is how we will continue to picture them. But at this point we introduce a distinction between three types of energy levels: the electronic, vibrational and rotational energy levels for a molecule. So particularly for a molecule. So for molecules as opposed to atoms of individual elements, the energy level or the energy itself is of three types, and for each of those types you have energy levels. So, and by types I don't mean potential energy, kinetic energy in that sense. It is all energy related to motion, kinetic energy, but within that let's say depending upon what causes this energy or what this energy is associated with, we have three types. So electronic, vibrational and rotational energy. So we'll look at them in detail now. So electronic energy is the electron repulsion or electron proton attraction, all those interaction between charged particles, to put it in a simple way. Whatever energy comes because of an attraction or repulsion between two charged particles, that falls under electronic energy. Vibrational energy, as the name suggests, comes from vibration of your electrons or atoms. What can be a cause of vibration is when two atoms or two electrons collide, for instance. That is vibrational, any vibration and the energy associated with it. Rotational energy, again as the name suggests, is rotation. So when an electron is moving in an orbit or when an atom moves, electrons have a spin, right? So that spin is associated with rotational energy. And the atoms in a molecule, especially if it's a gaseous element, something like carbon dioxide, the atoms are somewhat they have some freedom to move around in the material, right? So all that movement related energy falls under rotational. So what did we just see? Energy, especially for a diatomic molecule at least, is divided into three types: electronic, vibrational and rotational. So corresponding to each of these types you have separate energy levels, electronic energy levels, vibrational and rotational. So these energy levels correspond to the same electron. So the same electron has electronic energy levels, vibrational and rotational. They are three separate entities which coexist for the same electron. Now so we know that the entire stimulated emission and all that and population inversion and all that happens because of electron movement from one layer or one energy level to another, right? So which of these three types of energy levels are we talking about? In case of a carbon dioxide laser, it is a vibrational level. A metastable level is just another name for your pumping level, the level to which you're going to put electrons. So what does this thing say? Resonant transfer to a metastable level, which is a vibrational level, meaning in terms of electronic energy and rotational energy, my electrons are going to stay right where they are at the same energy level. It is only the vibrational level which is going to change. So if let's say my electron is in its ground vibrational energy level, ground level with respect to vibrational energy, I'll take it and put it in a metastable or a pumping level, again with respect to vibrational energy alone. So how is that choice made, or how do you make sure that the energy you give transfers only the vibrational level is beyond the scope of our syllabus? All you need to understand is there is some mechanism which makes sure that the electronic and rotational energy remains the same. Only in terms of vibrational level there is a population inversion which is being created. So this is an example. Here the long horizontal black lines represent electronic energy levels, a ground state and an excited state. The shorter black lines represent your rotational levels, and the blue lines in between are the vibrational energy levels. So let's take this quick exercise to sort of understand things better. Here's the figure, and indicate the molecular state which is electronically in the ground state, vibrationally the first excited state, and rotationally in the ground state. So electronically in the ground state is this long line here, vibrationally in the first excited state, so this would be the ground state vibrationally, this blue line, and this is the first excited state, so this, and rotationally in the ground state, the first small black line over here. So the ground state again for rotational starts here, so the first line here would be that. So you can see that there are three different lines we are pointing to, which means the three types of energy levels are discrete or separate entities. So why are we talking about this? Coming back to the carbon dioxide laser, what the point I'm trying to make here is it works the same as any laser. Pumping, stimulated emission, electron coming down, and all that is the same. The only thing to remember here is electron movement happens between two energy levels in the vibrational energy level set of levels. Electronically and rotationally it remains where it is. Output characteristics, this is the wavelength, continuous or pulsed, power greater than tens of kilowatts. So that was an overview of the carbon dioxide laser. Here we just take a small detailed look at the vibrational levels itself. So vibrational level is where this electron transfer is taking place, right? So we're going to be looking at this in a little more detail. So in addition to electronic transitions, the atoms may vibrate or rotate, which is why you have vibrational and rotational levels. Within an electronic level you have vibrational sublevels, and within the vibrational level you have rotational sublevels. So this is an electronic level, you have vibrational sublevels. Within the vibrational level you have rotational sublevels. Yeah, so and we are not going to look at electronic and rotational levels much here. Vibration, there are three modes and they are characterized by quantum numbers m and q, which stand for symmetric, bending and antisymmetric mode respectively. So in the symmetric mode, this is first your this is what your carbon dioxide molecule looks like. The blue circle is your carbon atom, the two yellow ones are the oxygen atoms. Now in symmetric mode, the movement happens like the expansion or compression of a spring. So when you hold a spring with both your hands and you pull, the left end travels to the left, the right end travels to the right. So they travel in opposite directions when you're expanding. And when you're compressing, the left end travels towards its right end towards the left. So again both ends are traveling in the opposite directions. That is analogous to symmetric mode. So in symmetric mode, this oxygen atom goes here, simultaneously this one goes here, then this one comes back here, this one comes back here, so opposite direction, and that is symmetric mode. In bending mode, the molecule bends as the name suggests. So the carbon goes up and the two oxygens come down, or the carbon comes down and the two oxygens go up. That is bending mode. Antisymmetric mode, again it remains straight, a horizontal line. Both the oxygen atoms move in the same direction. Either this moves right and this moves right, or this moves left and this moves left. So that is antisymmetric mode. So those are the three modes of vibration possible. And what are these quantum numbers here? 000 means it is in its normal state, and when it is vibrating, you have these three quantum numbers, out of which only one of those three will be 1 at any given time. The rest are all going to be 0. So if it is first one is 1, it means symmetric mode. If the second one is a 1, it means it's in bending mode, and if the third one is a 1, it means it's in antisymmetric mode. That is why SBA, symmetric, bending, antisymmetric. So these are the three different ways in which a carbon dioxide molecule can vibrate. Why are we studying about this? Because each of these modes of vibration requires different amount of energy. So the vibrational energy levels are arranged depending upon how much energy is required, which in turn depends upon which mode of rotation it is going through. So generally, bending mode requires least energy, symmetric is moderate, and antisymmetric requires the highest energy. So if you have three vibrational energy levels, the lowest of them would characterize bending mode, the middle one is for symmetric mode, and the higher one for antisymmetric. So that is just a quick look at the different modes of vibration.